and now that we've actually talked about the natural causes of climate change, we're going to now talk a little bit about what humans have done or what humans can do to change the climate. Just a quick review from the previous lecture. There's really only two ways that you can naturally change the climate. Either change the amount of sunlight that the Earth receives, or change what the Earth does to that sunlight. Neither process really is a quick process. Either one of those two processes usually takes tens, if not hundreds of thousands of years to occur. The only two exceptions are the sunspot cycle, which occurs every 11 years, or changing the composition of the atmosphere, which one volcanic eruption and boom, you can have global climate change. However, what about what humans are doing to the climate? Well, that's what we're going to uncover in this lecture. So, how are we the problem? Well, let's talk about it. So, what is the main cause of global climate change? Well, eccentricity, obliquity, precession, sunspot cycles, none of those things can really explain why the Earth is warming. Adding aerosols to the atmosphere would cool the Earth, and volcanic activity pales in comparison to the amount of human activity, at least as far as CO2 emissions are concerned. So what is the smoking gun? What is the main cause of climate change? Well, it all goes back to the greenhouse effect. So, if you don't remember the greenhouse effect, we talked about it back in Module 2. But I'm going to give just a quick review of it here. So, the way the greenhouse effect works is the same way that your car gets really hot in the middle of the afternoon. So let's say you park at De Anza College, and it doesn't even have to be a particularly warm day. Just park at De Anza College, close your doors, make sure your windows are closed, go to your classes, try not to fall asleep in them like I used to, and then come back to your car a few hours later. Well, your car is going to feel a lot hotter. Well, the greenhouse effect explains why your car feels hotter. Because the windows in your car let sunlight in. Once that sunlight gets into your car's interior, your seats, the steering wheel, the dashboard, all of that absorbs that heat and heats up. In turn, it increases in temperature. As it increases in temperature, it gives off more radiation itself. Now, here's an important thing though. The type of radiation that entered your car from the sun is what's called shortwave radiation. It consists primarily of visible light, near-infrared rays, and ultraviolet rays. On the other hand, the type of radiation that the interior of your car gives off is what's called long-wave radiation. It consists primarily of far-infrared radiation. It's the same kind of radiation that you and I give off. It's the same kind of radiation that the ground outside is giving off right now. And whereas those windows in your car were transparent to that incoming sunlight, they are opaque, meaning they block the outgoing long-wave radiation. Well, the greenhouse effect works the same way. There are certain gases in our atmosphere that act like the windows in our car, in that they let sunlight in, the sunlight heats the surface of the Earth up, as the Earth's surface heats up, it gives off more long-wave radiation, and those same gases trap the long-wave radiation. It keeps it stuck near the surface of the Earth. This results in an energy surplus near the surface of the Earth. The Earth is now giving off less heat than it's receiving. As a result, the Earth warms up. Now, the reason why it's called the greenhouse effect is because this is exactly how greenhouses work. This is why you're able to grow plants in cold climates, because you can build a house made out of glass, like this one here, that lets sunlight in, warming the building up. But the long wave radiation that all of these plants and the ground is giving off can't easily escape. As a result, heat gets trapped in here, it continues to warm up, and thankfully, that keeps these plants nice and warm. Now the good news is as they warm up, they give off more radiation, and eventually what happens is the amount of incoming eventually equals the amount of outgoing again, and a temperature balance is achieved. So thankfully these plants don't just continue to warm up until they reach infinity. That would be bad. So there's a balance that's achieved. Now, there are 4 main greenhouse gases that we are concerned about here on Earth. Now, these aren't the only 4 greenhouse gases, but these are the 4 common ones. And they are water vapor, methane, carbon dioxide, and ozone. Let me talk about each one of these really quick. Water vapor. This is defined as the humidity in the air. The more humid the air is, the more water vapor is in the air. Now, I'm sure that you've experienced days where it's so humid outside that your hair is frizzy, you're sweating and the sweat's not evaporating. Those are humid days where we have a lot of water vapor in the air. On the other hand, you've also experienced days where it's very dry outside and touching anything metallic results in a shock. That is a dry day. So as you can see, the amount of water vapor in the atmosphere actually fluctuates tremendously. And part of the reason why is because water cycles in and out of the atmosphere very quickly. Once it gets into the atmosphere, it quickly leaves the atmosphere. So water vapor doesn't really hang around. So we're not very worried about it. Now, if we do get more water vapor on average being absorbed into the atmosphere, that can have an impact, but we're not going to worry about that too much. The fact of the matter is that water vapor cycles in and out of the atmosphere very quickly. So we're not worried about it. Now what about ozone? Now, I know what you're thinking when you hear ozone. Oh wait, isn't ozone that stuff that keeps UV rays out? Well yeah, it's a good thing in the stratosphere. However, here near the surface of the Earth, ozone is actually considered a bad thing, and it is a greenhouse gas. It does a really good job of absorbing radiation that's leaving the surface of the Earth. However, the thing about ozone is a very unstable element, or unstable molecule, here near the surface of the Earth. And in fact, ozone cycles in and out of the atmosphere just about as quickly as water vapor does. Though rather than changing phases like water vapor does, it reacts with sunlight and other chemicals to produce other things that we're more worried about, things like nitrous oxide and so on. We're not going to talk about those here. So this also cycles in and out of the atmosphere pretty quickly, so we're not worried about it either. On the other hand, these other 2, carbon dioxide and methane, these are the 2 that we're most worried about. But why are we worried about these 2? Well, there are 2 key things. One, unlike water vapor and ozone, which cycle in and out of the atmosphere very quickly, once a molecule of carbon dioxide gets into the atmosphere, it can hang out there for years. And in fact, once it rises above the surface of the Earth, it gets away from trees, it gets away from anything that could quickly react it out of the atmosphere. Carbon dioxide very quickly can get to a place where it's reacting with nothing. And as a result, it can just hang out there. And in fact, it's believed that carbon dioxide can hang out in the atmosphere for over a century. Methane, on the other hand, it doesn't hang out in the atmosphere as long as carbon dioxide does, but it's much more potent than carbon dioxide. So these are the 2 we're going to talk about. First, let's talk about carbon dioxide. Now, how do we actually measure how much carbon dioxide is in the atmosphere? Well, the way that we do it is we look at an observatory in Hawaii called Mauna Loa. This observatory is 11,000 feet above sea level. Here's why we want to do it here. We want to do it here because it's away from any urban influence. If we were to do it in, say, downtown San Jose, during the daytime, carbon dioxide concentrations would be really high. Why? Because everybody's out, people are driving their cars, carbon dioxide spewing out of them, people are burning fires, there's all kinds of things releasing carbon dioxide. At night, carbon dioxide concentrations would drop down again as people aren't driving and so on. So we want to get away from any of those localized signatures. Instead, we want to go somewhere where carbon dioxide concentrations are well mixed. Now here's what that means. What that means is that the carbon dioxide concentration doesn't change from one place to another. Rather, higher up in the atmosphere, carbon dioxide is believed, and this is not just believed, it's actually supported with data. It's known to be well mixed, which means that, again, it's uniformly spread out. It's the same concentration all around the world. So we want to do it high above urban influences, and we also want to do it somewhere out in the middle of nowhere. So Mauna Loa has been really the most famous example of this. There are other observatories that have also taken carbon dioxide concentrations, and they've all actually come out with pretty similar results. Now, with this said, we've determined after over 150 years of observations that from 1850, which is right around the heyday of the Industrial Revolution, that was right around the time that we really began to transition from an agriculture-based society to a more industrial society, and really the late 1850s and early 1900s were really when that happened, to today, carbon dioxide concentrations have increased from 280 parts per million to over 400 today. And in fact, it's now easily above 400. It's closer to 404, 405. Well, this is alarming. And the reason why this is alarming is because before 1850, carbon dioxide concentrations maintained relative stability. They didn't rise and fall too much. However, over the last 150-ish years, they've risen substantially. And the reason why this is because of increased human activity. We'll talk more about what that increased human activity is in a few more slides, but this is even seen in more recent years, since the 1960s, through Mauna Loa, in a graph called the Keeling curve. This is the Keeling curve. And this was actually an outdated graph. The more recent graphs actually show this closer to 404, 405 parts per million. But we have been gradually rising. From the late 1950s, carbon dioxide concentrations were around 315 parts per million. Well, if you take a look, every year, they're steadily rising to now on the precipice of touching 400 parts per million and slightly beyond that now. Now, before I continue on, one of the things you might notice about this graph is it's spiky. It's kind of like Bart Simpson's hair in a way. If you don't know who Bart Simpson is, Google him. But it's very spiky. Up, down, and so on. Now, why is that? Well, the reason why that is because of photosynthetic activity. One of the biggest carbon sinks, one of the biggest things that removes carbon dioxide from the atmosphere is trees. And what actually happens is when you have more trees, higher tree activity, you have more photosynthesis happening, the amount of carbon dioxide in the atmosphere actually decreases. Well, trees across most of the world are seasonal, meaning that they are alive and kicking in spring and summer. Then fall rolls around. And when fall rolls around, many trees shed their leaves and go into hibernation. They stop doing photosynthesis. As a result, carbon dioxide isn't being consumed by them, and carbon dioxide concentrations go back up. So they go up in the fall and winter, down in the spring and summer. Up in the fall and winter, down in the spring and summer. Up in the fall and winter, down in the spring and summer, and so on. So that explains why you see this variation of up, down, up, down, up, down. The ups represent fall and winter seasons when photosynthetic activity is low. The downs represent spring and summer. That's when photosynthetic activity is high. So if you ever have anybody tell you, well, the past few months carbon dioxide concentrations have actually gone down, well, yeah, they're supposed to. It's a natural cycle. It's a seasonal cycle. But if we actually look back further, and we don't have Keeling curve-like data, we don't have Mauna Loa data from 200, 300 years ago. Mauna Loa didn't even have an observatory 200, 300 years ago. So in order to understand previous carbon dioxide concentrations, we have to look at ice core data. Now, ice cores are very useful because whenever snow lands on the surface of something, that snow is actually enriched with air in the atmosphere. Now, as snow then absorbs that atmosphere, and then more snow falls on top of it, if it's in a place where snow doesn't melt, so any place near the poles, it's permanently locked in. Those gases are permanently locked in. So we can look at ice cores, basically these long tubes of ice, and look at each layer to tell us what the atmospheric composition was like then. Well, if you look over the past 1,000-ish years, what you noticed is that carbon dioxide concentrations were relatively steady. If you look here, carbon dioxide concentrations hung around 270 to 290 parts per million. They didn't really vary much. And then we reached the 1800s. The 1800s, the early 1800s, marked the beginning of the Industrial Revolution, and that was when we learned that when we found all this stuff in the ground, we were able to burn it. That created a lot of heat, that created a lot of energy, and then we were able to use it to fuel our cars or use it to create electricity and so on. Well, the Industrial Revolution began in the early 1800s, and it really took off in the mid to late 1800s, especially after the US Civil War, and industrialization, urbanization really began to take off in the late 1800s. And as that happened, carbon dioxide increases became much, much, much more apparent. And then these dotted lines represent more more official instrument observations. But if you take a look, ice core data still actually gives us pretty similar results. So there are more uncertainties in ice core data, but they're still pretty accurate. Now, currently, we're off the scale. We're up here. If you take your finger and you touch the top of your screen, that's where carbon dioxide concentrations are now. So as you can see, we've gone up quite a bit in a short period of time. Well, how does this actually look compared to hundreds of thousands of years ago? Well, the frightening thing is that whenever carbon dioxide concentrations, which are right here, whenever they've gone up, temperatures have also gone up. And you see that many times here. You saw it about 325,000 years ago. Temperature shot up, carbon dioxide shot up. 240,000 years ago, carbon dioxide went up, temperatures went up. 135,000 years ago, temperatures went up, carbon dioxide went up, and so on. The other thing that you notice, though, is that these carbon dioxide concentrations were all substantially lower than where we are now. Take your finger, put it at the very top of your monitor. So not just the screen, but actually the top of the monitor itself. That's about where we're at now. So we are way off the scale now. Well, if this was a predictor of what could happen, imagine what temperatures are going to do over the next approximately 20, 30, 40, 50 more years. We could see substantial jumps in temperature in a very short period of time. That's what's so alarming about this. The other thing that's so alarming about this is that these changes in carbon dioxide concentrations, they take upwards of 3, 4, 5,000 years to happen. So for example, the bottom here, 180 parts per million. To go from there to our current 280 parts per million took approximately 6, 7-ish thousand years, maybe a little bit more than that. To go from this bottom to where we're at now took thousands of years. Yet we have jumped up another 120 parts per million in just 150 years. That's alarming. So that's one of the reasons why we are so sure that this is happening and we're so concerned about it. It's not just that the Earth is warming, it's not just that carbon dioxide concentrations are going up, it's how quickly they're going up. Now, with this said, the greenhouse effect and greenhouse gases are a good thing. Without them, the average temperature here on Earth would be substantially cooler. However, with them, the average temperature is a lot more bearable. But have you ever heard of too much of a good thing? Think about your favorite food. Imagine if you ate your favorite food for breakfast, lunch, and dinner every single day without fail. What that would do to your body. That'd be a bad thing, right? Well, the same thing with greenhouse gases. The more greenhouse gases we have, the hotter the Earth gets. And that could be a bad thing for many things. More greenhouse gases equals more heat trapped in equals warmer temperatures. So yes, we are concerned about this. Without greenhouse gases, as I mentioned, the balance of outgoing to incoming would be achieved at a temperature of approximately 0 Fahrenheit. With them, it's achieved at a temperature of 59 Fahrenheit. Now, carbon dioxide is the main thing. It's the one that we're the most concerned about. However, it's not the only one that we're worried about. Methane is also very concerning. And methane emissions come from all kinds of things. Agriculture, all those cows, they burp and fart. I know it's funny and gross, but they burp and fart. That releases a lot of methane. Our oceans release a lot of methane. And when we release methane into the atmosphere, it's not nearly as abundant as carbon dioxide, but it has been still going up noticeably. But that's not what's scary about methane. The thing that's scary about methane is that methane is 21 times as potent as greenhouse gas. Or sorry, I apologize. It's 21 times as potent as carbon dioxide. What that means is if I have one molecule of methane, it can trap in 21 times as much heat as one molecule of carbon dioxide. 21 times as much. So having methane in our atmosphere is a very concerning thing. And as we grow more beef, as we increase our agriculture, we are increasing the amount of methane that's being released into our atmosphere. And if we don't do something about it, that can cause runaway warming. So even though methane isn't as abundant as carbon dioxide, it's 21 times as potent. So it's still very concerning. Now, with all of that said, with the increases in carbon dioxide, with the increases in methane, and there are other things that have changed as well. Changes in land use is one of the big things. We've, in a sense, paved paradise and put up a parking lot. We'll talk more about that in a few lectures. By doing that, we've also led to warming. We've decreased the amount of vegetation we have on Earth. That's decreased the amount of carbon dioxide that can be absorbed. With all of that said, it is extremely likely that observed warming has been caused by human activity. This is from the latest IPCC report. The IPCC stands for the Intergovernmental Panel on Climate Change. This actually represents the world's most talented climate scientists from all across the world, developed countries and less developed countries, doing cutting-edge research all around the world and taking all of their conclusions, working out the differences, and figuring out what's happening. And after doing all of that, this body, this panel, released a report stating that it is extremely likely, with 97% certainty, that humans have had at least some part in the warming that we've experienced, and that we've warmed anywhere between 0.85, give or take 0.2 degrees Celsius. So anywhere between 1.05 degrees Celsius and 0.65 degrees Celsius. So little over half a degree to a little over a whole degree. That doesn't sound like a lot of warming, but that's actually a tremendous increase in temperatures. That's an increase of almost 2 degrees Fahrenheit in just a century. That's a big change in a short period of time in the global average temperatures across the world. That is very alarming. Now, with that said, what could happen? In addition to diagnosing the problem, determining what's been happening, the IPCC has also made scenarios for what might happen. And each one of these scenarios is based on the average temperature at the turn of the century, at the end of the 20th century. And all of these scenarios can be grouped up into two categories. Well, first, the baseline scenario, assuming that carbon dioxide stayed constant, would commit us to an additional 0.3 to 0.9 degrees warming. So if we kept carbon dioxide constant, no more carbon emissions, we just kept it where it's at, we would commit to almost a full degree of warming already. So we're already committed to up to another degree of warming. Well, these other two scenarios I'm talking about are split up into what are called A scenarios and B scenarios. A scenarios are scenarios focused solely on economic growth. Here, we don't care about what we do to the environment. It's all about the economy. It's all about increasing productivity. It's all about making more money. It's all about economic growth, which is a good thing. Economic growth is a good thing. But in these scenarios, that's the primary focus. Environmental sustainability is not considered. In this case, we have 4 different scenarios. The first set of scenarios are called the A1 scenarios. These are globalized efforts. In this case, the world as a whole focuses on one concerted effort for economic growth. And there are 3 A1 scenarios. They are A1F1, which is fossil fuel intensive, meaning we're just going to burn all the fossil fuels we have, keep doing it, keep doing it, keep doing it. A1T represents no fossil fuels. We're going to completely throw away fossil fuels. And A1B is balanced. In the A1F1 scenario, we are committing ourselves to at least 2.5 to potentially as much as 6.5 degrees Celsius in warming. In the non-fossil fuel scenario, we're committing ourselves to 1.5 to maybe as high as 4 degrees Celsius warming. And then in the balanced scenario, a little over 1.5 to approximately 4.5 degrees warming. So these are the globalized efforts. These are globalized efforts focused on economic growth. The other set of A scenarios are called the A2 scenarios. Rather than focusing on economic growth as a globe, instead, individual nations focus on their own economic growth. In these cases, we could see as much as 2 to 5.5 degrees warming. So, of the A scenarios, the worst one by far is the A1F1 scenario. This is fossil fuel intensive. This is at all costs burning whatever we need to. We want economic growth. This is really the trajectory that we're on right now. This one, the A1T, is if we completely give up fossil fuels, and A1B is transitioning in a way. This is kind of like the hybrid car of the world. This is like the gas guzzler, this is like the Tesla, this is like the hybrid. And then A2, as I said, rather than being globalized, it's localized, meaning every country does different approaches. Now the B scenarios, rather than being focused on economic growth, they are focused on climate sustainability. They are less concerned about growing our economy, making more money, stronger businesses, and they're more focused on creating a stable environment. And of the B scenarios, there are two of them. The B1 scenario is the globalized effort. In this case, we as a globe say, okay, not only are we going to not use fossil fuels, but we're going to actually focus on, in addition to that, also being more sustainable in our efforts. So we're going to increase things like recycling, we're going to transition to more eco-friendly things, more green energy, and so on. If the globe as a whole comes to a globalized agreement, which we have actually, we would see anywhere between 1 to 3 degrees Celsius in warming. If instead of coming up with it via a globalized effort, we instead told each country, hey, just come up with your own plan, and every country did its own thing, we would see approximately 1.5 to almost 4 degrees warming. So by far, of all of these scenarios, the B1 scenario is the best one. But it's also the most politically difficult one because, one, it needs to be globalized, meaning that the entire globe has to agree on one approach. And we all have to commit to that approach, and we all have to stick to that approach. It's also difficult because, obviously, not every country is created the same. You have industrial superpowers like the United States, like China, and then you also have a lot of developing countries, many places in sub-Saharan Africa, many places in Eastern Europe, many former Soviet countries, many Middle Eastern countries that are now developing, they're industrializing, and this is an issue for them. So it's the hardest one to achieve, but it's also the best one. If we left it up to everybody just to come up with their own efforts, we're committing ourselves to almost an additional degree of warming. But again, even the B2 scenario is better than practically any of the A scenarios. Now, One thing I should stress before I end this lecture, though, is that all of these scenarios, including keeping carbon dioxide concentrations constant, all of them commit to at least some warming. So our Earth is going to continue to warm. There's no doubt about it. I would bet the farm on it. There's no doubt about it. Our Earth will continue to warm. However, the difference is, can we make the warming something that we can deal with? Or can we make it something, or are we going to make it something that's much, much more harmful, much more intense? And to understand the worst case scenarios, there's a few movies I would suggest watching. 6 Degrees Could Change the World is a really good one, and in fact, if you're in my online class, chances are I've probably assigned it as an assignment. If you're watching this just to watch it, then obviously you don't have to do that. But another good one is called 2100, and it's a what-if scenario that was done about 7 years ago. It's pretty interesting. So I'd recommend checking either one of those out. Now, with all that said, why is climate change so scary? What are the threats of climate change? What are the consequences of it? Well, we're going to talk about that in the next lecture. So until then, thank you for watching.